Construct a triangle ABC such that the distance between A and B is 8 centimeters. The distance between B and C is the same as the distance between D and C is 5 centimeters. And we're given the point A here. Alright, so the construction is shown here. So we want to pick a point B such that the distance between A and B is 8 centimeters. Okay, so we can see that we can put a compass point at A, set it to 8 centimeters, draw an arc. So this distance is 8 centimeters. Next we can set the compass to 5 centimeters. Put the compass point at A, draw an arc whose radius is 5 centimeters. With the same extension on the compass, we put the compass point at B, draw a second arc. Okay, so the second arc also has a radius of 5 centimeters. Next we join A to the intersection of the two arcs. So this distance will be 5 centimeters. Okay, because any point on this arc here is at a distance of 5 centimeters from A, and any point on this second arc is at a distance of 5 centimeters to B. So we connect this point down to B. Next we will construct the image of the triangle ABC under the axial symmetry in the line AB. So here we have the image of triangle ABC. That's this triangle here under axial symmetry in the line AB. So we want to basically fold this triangle over the line AB, get the mirror image of it in the line AB. Now the image of A under axial symmetry in the line AB is just A. A is mapped onto itself. B is also mapped onto itself because B is on the line AB. To get the image of C, we project down through this line at right angles and go out the same distance on the other side. So to do that, you could use a straight edge and set square and draw in this dotted line. Line your straight edge up with the line AB and just use a set square to draw in this dotted line. That's one way of doing it. Another way that you could do it is simply use your compass. Make the same construction down here as you did above the line AB. Just draw two arcs of radius 5 centimeters. So put your compass point at B, set the compass to 5 centimeters and draw in an arc whose radius is 5 centimeters, of course. With the same extension on the compass, you put the compass point at B and draw a second arc whose radius is 5 centimeters, of course, and just connect everything up. That will ensure that this distance is the same as this distance, because we have two congruent triangles here, so their perpendicular heights will be the same. So this point here is the image of C under axial symmetry in the line AB, so we can call it C prime. A prime is just the same as A, and B prime, the image of B, is just the same as B. Justify the statement AC prime BC is a parallelogram, where C prime is the image of C under the axial symmetry in the line AB. Okay, so how do we prove that this quadrilateral is a parallelogram? Well, we have the lengths of the sides. In any quadrilateral, if the opposite sides are equal, then the quadrilateral is a parallelogram. So this side is equal to this side, a pair of opposite sides, and this side is equal to this side, another pair of opposite sides. So, okay, why does it follow that if opposite sides are equal, then our quadrilateral is a parallelogram? Well, these two triangles are congruent, because the three sides of each of these triangles are equal to each other. Okay, this side equals this side equals this side, and of course this side here is the same in both triangles. It's a common side of both triangles. So that congruency condition is abbreviated side, side, side. Three sides are the same. in both triangles, and if the three sides are the same, the triangles are congruent. They're equal in every way. So in particular, the angle that's opposite this side, namely this angle in here, is equal to the angle opposite the equal side in the other triangle. Now all four sides are equal in this particular quadrilateral, but in general all four sides might not be equal. Like, let's look at this quadrilateral here. Opposite sides are equal, but this side is not equal to this side. So again, we could still prove that this thing is a parallelogram by drawing in the diagonal. So we get two congruent triangles because the three sides are the same. This side equals this side equals this side, and of course this side is common to both triangles. So by side, both of these triangles are congruent. And then we could consider angles corresponding to the equal side. So the angle opposite this side is here in this triangle, and the angle opposite the corresponding side in the second triangle is here. So these angles would have to be the same since the two triangles are congruent. But now we can invoke the idea of alternate angles, alternate or z angles. So we formed a pair of z angles, and if these angles are equal, then these sides must be parallel. This line must be parallel to this line here. So that's basically what we do here as well. This is just a more general situation, but it's the same idea, of course. This must be parallel to this because we formed a pair of z or alternate angles. And similarly for the other two sides, we can easily show that they're parallel using a very similar argument, just like here. This angle is opposite this side here, which is the same as this side. So we're talking about these two angles now. They're equal into congruent triangles. So we formed a pair of z angles. So this line must be parallel to this line. So we've proven that if opposite sides are equal in a quadrilateral, then the quadrilateral is a parallelogram. In the acute angled triangle ABC, AP is perpendicular to BC, BQ is perpendicular to AC, and CR is perpendicular to AB. So here we have the three altitudes or heights of this triangle. Okay, so this line is a height or altitude. This line here is another altitude, and this line here is an altitude. Now we know from previous videos that the three altitudes of any triangle are concurrent. That means that they pass through a single point. Now we want to prove that these three angles add up to 90, so let's just identify these angles and use simpler labeling convention. So what about angle ABQ? Well, one arm is AB and the other arm is BQ. So let's call this angle X. BCR is this angle here, I'll call it Y. And CAP is here, let's call it Z. Okay, one way to prove this is to first of all consider the big triangle ABC and its angles. Okay, so we need to consider the three angles of the big triangle. We know that they add up to 180 degrees. So this angle plus this angle plus this angle is 180 degrees. The three angles in any triangle add up to 180 degrees. So let's give a name to these three red angles. I've used X, Y, and Z. I could use A, B, and C, but A, B, and C have been used to label the corners. So I'll call this one L. Actually, I don't want to use L because it looks like the 90-degree symbol. Let's call it P. Well, P is already used, so let's call them E, F, and G. I'll call this one E, this one F, and this one G. So this is just, it's easier to see what's going on rather than using the, the points to describe the angle. Much easier to see what's going on. I just use a capital letter to describe the angle. Okay, so obviously if we add up these 6 angles, we get 180 degrees. We get the angles in the big triangle. X plus E plus F plus Z plus Y plus G equals 180. So we note down that fact. We use the fact that the 3 angles add up to 180. But how can we connect the red angles to the black angles? Well, let's look at the right angle triangles. So let's start with this triangle here. Let's look at Y plus G. How is it connected to Z and this right angle? Well, these 3 angles add up to 180 degrees. Since one of the angles is 90 degrees, these 2 must add up to 90, because 90 plus 90 gives us 180. So Z plus G plus Y must equal 90 degrees. Okay, so we did it for this right angle triangle, and then we do something similar for the other 3 right angle triangles. So now let's take this right angle triangle. So this angle here, X plus E, plus angle Y must equal 90. And finally we have this triangle here, F plus Z plus X must equal 90. Okay, so we have all this information. So is it enough to answer the question? Is it enough to prove this statement here? Well, we could add these 3 equations together and we get one big equation that might look something like this here. We can use the fact that this statement is true. Okay, so we could add the left hand sides of these 3 equations together and set it equal to the sum of the right hand sides. So if we add the left hand sides, what do we get? How many z's do we get? We have 1z plus another z, that's 2z. We have this g. We've y plus y, that's 2y. Okay, how many x's do we have? X plus x is 2x. So I'm just adding the left hand sides of the 3 equations together. We need the E and the F. So that's what we get, and we add the right hand sides, 90 plus 90 plus 90. That's 270. Now we are not interested in the red angles, E, F and G. Okay, they're the red angles in the diagram. We're interested in the sum of X, Y and Z. So if we can get rid of these things, we hopefully can prove our result, X plus Y plus Z equals 90. So what we could do is take this equation here and rearrange it. So E plus F plus G is on the left hand side and everything else is on the right hand side. So we subtract X, we subtract Z and we subtract Y from the right hand side, from 180. The next thing that we could do is just plug in for E plus F plus G, plug in this expression here and then into this equation up here. Okay, so I'll write this down again, 2z, but instead of G plus E plus F we have this thing here. So I'll write this thing out now. Okay, that's instead of the G plus E plus F. This thing has gone in and we're left with 2y plus 2x. That's equal to 270. See, we have an equation just involving x, y and z. That's what we're after. We want to prove this thing up here. So hopefully this equation will lead to this one up here. So we have 2z minus 1z, that's 1z. 2x minus x is 1x. 2y minus y is 1y. and we bring the plus 180 over. 270 minus 180 is 90. That's what we have to prove. Okay, here's another way that we can prove this theorem. What we could do is look at this angle here and this angle here. The sum of them is 90 degrees. This angle is Z actually. Let's give this angle here a name. I could call it ACB, but that's a bit cumbersome. So I'll call this angle M. So Z plus M must equal 90 degrees because this is a right angle. Okay, so we're looking at just this triangle here. Okay, so we have Z plus M equals 90 degrees. It's looking at triangle APC, but we can now look at triangle AQC. M is also part of this second right angle triangle AQC. So M plus this angle here must add up to 90 degrees. These two plus 90 degrees gives us 180 in this right angle triangle, triangle BCQ. So let's give this angle here a name. Let's call it N. So N plus M equals 90 degrees. Again, it's because the fact that we have a right angle triangle and these are the other two angles in it. But notice something here. Z plus M and N plus M are equal to the same thing, namely 90 degrees. So they must be equal to each other. Z plus M equals N plus M. And that means that Z must equal N, of course. We subtract M from both sides. So we've established that this angle is the same as Z. Now see that this angle here in green is common to triangle BQA and right angle triangle CRA. So we can use that fact. We can say X plus this green angle. Let's give it a name. Let's call it T. X plus T must equal 90 degrees because we're looking at this right angle triangle here. Okay, this angle is 90 degrees, so these two corners must sum to 90. So you can write in a reason, of course, which I didn't do for the previous ones, but if you want to write it in, you can point out that this angle is 90 degrees and we are working in this triangle. Okay, so now let's look at this right angle triangle here. These two angles must add up to 90 because of this right angle, of course. So that's T plus this one here now. What do we call this one here? Well, we could give it a name, but we can also see that it's just angle M, the red angle, minus the black angle, angle Y. Okay, so that's this angle in here. It's M minus Y. Okay, it's the red angle minus the black angle. So angle T plus this angle must equal 90 because this angle is 90. So again, two things equal to the same thing must be equal to each other. So X plus T must equal T plus M minus Y. So X is equal to M minus Y. Okay, let's see now. Let's add up the three corners of the big triangle. They add up to 180, of course. So we have X plus N here. We were after calling this one T. And what about this one here? Well, we called it M. Okay, we somehow have to prove this thing here, so we don't want N, M, NT or M appearing in this. We want to replace them so that we just have an equation involving X, Y, and Z. So instead of N, we can write Z. Now I'll come back to T. What about M? Well, if we rearrange the second equation, we see M is just X plus Y. Just bring the minus Y over. Okay, so this equation just comes from the three angles in the big triangle equaling 180. Or in any triangle, of course, equal to 180. The problem here is T. Let's look at this right angle triangle here. What's this angle? Well, it's the green angle t minus the black angle z. So this is t minus z. If we add t minus z onto x plus n, we get 90 degrees because this is a right angle. But what is n? Well, n is just equal to z, so we can get rid of that n. Okay, the z's cancel here, so we see that if we shift the x over, t is equal to 90 minus x. So I've got t in terms of x, so I can sub it in here. So we're going to get x plus z plus 90 minus x for t plus x plus y equals 180. So now we've got rid of everything. We just have x, y, and z in this thing. These x's go out. And if we just subtract 90 from both sides, we get z plus x plus y, or x plus y plus z, equals 180 minus 90, which is 90. That's what we have to prove.